Okay. So exam 12, right? And it'll be everything from the last exam up through confounded factorials. Are there any questions? There should be another homework assignment that's out there. It'll be on incomplete block designs. Okay, so last time we started talking about the analysis of incomplete block designs. And before we really get into the analysis, there's two ways to analyze data from incomplete block designs. One is assuming blocks are fixed. That's called the intra-block analysis. In other words, no information in the blocks is really contained in the means. Whereas we also can use the mixed model approach, assuming that blocks are random. And in that case, it's called the combined intra-block analysis for historical reasons. But before we go on to that, what I'd like to do is talk a little bit about how you calculate the efficiency of these things. And if you remember last time in the preliminary analysis, the ANOVA looked like this. The preliminary analysis, if this is a resolvable design, I'll have REP with R minus 1 degrees of freedom, treatment with T minus 1, and then blocks, incomplete blocks, nested within REP, D minus 1 times TR, and then finally the error. And the error is basically just everything else, all the other degrees of freedom that remain. And so how you can get that is, well, you just get the degrees of freedom that you get from a randomized complete block design, which would be R minus 1 times T minus 1, minus the degrees of freedom that you use to correct for the blocks. Okay. So this is minus B minus 1 times R. Okay, so that's the ANOVA that I gave you. Now, what we do is we get the mean squares for this. We get the mean square for error, and we get the mean square for block. Okay, so for the first analysis that we do, then we, this is a preliminary analysis, we do intra-block analysis in this way. Now, what we calculate is we calculate the efficiency factor. The efficiency factor is B minus 1. You basically just get the error sum of the squares that you get if you analyze it as a randomized complete block, divided by then basically the degrees of freedom from the incomplete block, which is T minus 1 times MSE. We talked about calculating this efficiency factor the other day. We also said that if the degrees of freedom were small, for example, if degrees of freedom for the incomplete block are, say, less than 10 or so, then you want to adjust this. Not give the adjusted degrees of freedom for these in the past. Okay, so in your preliminary analysis, you calculate this analysis of variance just using least squares. And you can calculate this efficiency term here. And so what this is it's like the error sums of squares from the randomized complete block over the error sums of squares from the incomplete block. And so if the efficiency factor is greater than 1, then the randomized or the incomplete block design is an efficient design. And so normally what people do is if the EFF value is greater than 1.2, then the incomplete block design is a good design. Okay? Then use the incomplete block design in the future. If not, then you're wasting your time. Maybe not even use it. Just use a complete block design. Okay? If not, just use RCBD in the future. I was talking about, we can use the same computational formula for efficiency of a confounded factorial, because remember the confounded factorial stuff would be, in the whole plot, would be the block the rapid block nested thin wrap. So we could use the same ideas to calculate, explicitly calculate efficiency for confounded factorials. And you know, I told you the example that one of the students, Angela Vestis, I helped with a while back. She was getting an efficiency when she did this of almost 2. Okay, so we're over here at 120. Well, she did a lot better than that. So in the future, then I'm encouraging her advisor to use incomplete blocks if they have experiments that have more treatments than just 5 or 10. Okay, are there questions on this? Okay, so the types of analyses of incomplete blocks. There's 2 types of analyses. One is blocks fixed. This is just a fixed effect analysis. A fixed block effect, just totally least squares. It's just a least squares analysis, also called the intra-block analysis. Intra-block analysis. Okay, and the other method is blocks are random. And what this is the mixed model. And this is called the combined inter-block analysis. Combined inter-block analysis. Inter-block analysis. And so we'll talk about both of these here. Now, last time I can't remember, I didn't pass out this handout here, did I? I don't think I did I? Doesn't look familiar, I guess. Okay, so let's do both of these and put some matrix algebra in it, so it's kind of understandable here. Okay, so now just first of all, I'm going to use SAS to talk about this. And then we'll talk about R a little bit here. So what I'm going to do first is I'll talk about just the simplest possible infinite block design. I think I talked about this right at the beginning of this section on incomplete blocks. The simplest possible incomplete block design is where I have 3 treatments and I have 3 blocks. And the experimental unit per block is 2, and I'm going to have 2 replicates per treatment. And so the first block would have treatments 1 and 2 in it. The second block would have, or in the example here, let's put A and B. First block would have A, B, second block would have A, C, and the third block would have B, C. Simplest possible incomplete block design you can have. And so I'm putting some numbers on these. Okay, so I'm going to put, let's see, the first value is a block, second value is a treatment, third value is the response. And then it goes on. The fourth value is block, fifth value is treatment, and the sixth value is Y. And it just repeats that way. In SAS, you can use the double @ sign to hold on to a data line, okay, in this way. Okay. So the values here for the first one is, what is it, 6, 8. What is it? 2 and 11?
7 and
7 and 11, right. 7 and 11. And then the last one is, what, 9.5 and 12.5? Okay. So that's what we're going to analyze. Now, if I'm going to do, use my approach I'm talking about, let's just do the intra-block analysis first. That's just using least squares. Okay, and that's what GLM gives you. Now, you can get GLMX to give you, this would be with no blocks random. It should give you, in method equal type 3, it should give you everything you need in GLMX or in mix. But I'll just do it with GLM because lots of people still use it. Okay, so this is the intra-block analysis. And so notice that there is no replicate in this. Okay? This is not a resolvable design. What is a resolvable design? resolvable incomplete block design. John, you guys use them all the time.
Each treatment occurs a equal number of times across the set, or
Well, if each treatment occurs equal number of times, that's what people call balance. No, but George has got, well, he does do some alpha analysis, always moved to augmented designs, but it's where you have all your treatments in a complete that's a complete replicate. And so you have all your soybean strains in a complete replicate, and you break that into incomplete blocks. So there's no complete replicates here. A complete replicate is one set of treatment combinations you show up exactly once. Doesn't happen. The model here is just simply y is equal to mu plus the block effect plus the treatment effect plus error, right? There's no replicate in here, so it's not resolvable. Well, it doesn't make any difference if we can use this model, and that's what I'm doing here. And the least squares, we just say y equals v for the block and t for treatment, and then we get the LS means, and we can say in GeoLab we can say random, which factor is random. We're going to do this, and we get expected mean squares from this, and we can calculate the variance component for block if we want. Okay. So once we have that block variance component, then we can actually compute the mixed model. Okay, so this is just a simple intra-block analysis. We'll look at that in a minute. But once I use the intra-block analysis, I can calculate the block effects. And you'll notice down below at the bottom here, I'm calculating, here's the error mean square, 1.67. And here's the block variance component, 0.75. Now from the intra-block analysis, I can calculate these. These are ANOVA estimators for the variance components. I can plug those in up here. Here's the variance component for block called sigma block in the IML. Here's the mean square error, right? And I'm going to put these together in the regular mixed model. Here's the X matrix for the fixed effects. Here's the Z matrix for the random effects. Now here's the covariance matrix for the blocks, for the random effects. Here's the covariance matrix for the residuals. And now I can put my V matrix together, right? We've been talking about this over and over, right? Right, you put this in and you get X prime B inverse X, so that's just this inverse matrix, and there's my beta tilde, right? So this should be all duck soup to you, right? This is not hard. Okay, and we're going to test hypotheses. First of all, we're going to estimate some things. The means we're going to estimate are going to be just the LS means. And so here are the K vectors that you use to get the LS means. This is a difference between I guess it's LS mean 1 and 2. Okay? And so I'm sorry, that's LS mean 3. And then here's a difference between LS mean 1 and 3. So we can calculate all these LS means and their differences and just plug those in. We can get the values and we can get their standard errors very easily. To get the F test for quality of treatments, we just use that big F formula and just plug in it. We have to get a big matrix for making all the comparisons, and that's appropriate. Okay, just a review. Okay, well that's the same thing as if you would do proc glim mix or proc mix. They are exactly the same thing in this particular situation. You say proc glim mix and everything else would be the same. Okay, well we can use the estimate statement to estimate the difference between the two and just use the statement over here, LS means, to give you LS means. Okay, so it's just doing exactly the same thing as what you've done here, but it doesn't really take too much effort to calculate it with matrices. So any questions on this? Okay, so what does the output look like? Well, let's look at the IML output. Okay, so here's my X matrix with the restrictions. And what restriction am I using here in that X matrix? That's fair game all through this class, right? What restriction am I using? There's only two we already talked about, was set to 0 and sum to 0. This is sum to 0, it's got -1 in there, right? Otherwise, we just have zeros and ones everywhere, right? Okay. We don't need to put a restriction on the Z matrix or random effects, which is kind of interesting. Okay. And so, okay, here is this is the variance, covariance matrix for the random effects. Number 0.75 is the variance component. This is just basically sigma square I. So this G is just sigma square I. So it's sigma square B, or the block effect, times I. That's what G is. Okay, and then the one below it let's see, there's the R. So this is just sigma square. This would be only what? 3, because there's only 3 blocks. Sigma square, which is the mean square error, times the number of observations. In this case, it's going to be 6. So this is going to be our R matrix. Okay, and that's what this thing is. And we can put those together and get a big V matrix. Here's the big V matrix, and then you calculate, which you notice is block diagonal. These are 2 by 2 block matrices. Why? Because I have 2 units in a block. So here are the 3 blocks. Block 1, block 2, block 3. Okay, so then we get the inverse, and now I can estimate all my LS means, and I can get my F value. So here's the inverse up here. This is x prime v inverse x, and then the beta tilde, and then here are the LS means and standard errors, and there could be exactly what you get out of glue mix or mix, or for that matter, LS means in R. Okay. And then there's the difference, which is just a contrast, and then the standard error of that also, and then finally here's the F value. And so these will be the values you'll get out of either glue mix or mix, or from the LS means that you get from L and R, because it's a mixed model formulation. Now, the mixed output, it'll give you what the variance component estimates are. There's a 0.75, exactly what we estimated. In this simple case, it'll be exactly the same. And this is the mean square error estimate, okay? And then it'll give you all these other things that are, I think, on the next page. Yeah, I'll give you LS means, the F test, and all these kinds of things. So here's the F test. It'll be exactly the same as we had before. Let's see, where is it? Where's the F? There it is. Okay, here's the F test. 46.8 exactly. Here's the differences, the standard error, and here's all the LS means, and standard error is exactly the same. Okay. Yeah.
So you said before that the Z matrix doesn't need restriction. And why is that?
Well, because you're really not estimating. We like to invert it now, do we? We don't invert the Z matrix. Where it comes in is our estimator has x prime v inverse x, inverse x prime v inverse y. Now, in the old formulation, remember we had to invert x prime x inverse, right? Well, we don't ever have to inverse ZZ prime. We never inverse that. Okay, so we don't need to worry about it. Okay, remember what the variance covariance matrix is. In the simplest case, it's sigma squared times the block times ZZ prime plus sigma square I. Okay, when we invert this whole thing. That's what this is. It's the whole thing we invert, not just this ZZ prime. Okay? So just the math comes out of it. But when you did fixed specs, you got to worry about that. Okay? And essentially, why? Because you're estimating fewer things with variance components. Is really what it comes to. Okay, good question. Other questions? All right, well, how do we do this in R? Well, here I'm reading in the data a little differently. That's reading the car package in LME4 because it has the LMER function I want to use. Okay, and I create a frame, and now the intra-block of that. This is just a least squares analysis. I can use LM. Okay, and there's my model. Y was block plus treatment. Keyboard, I guess that's order of treatments. Now, the ANOVA, you can use the ANOVA function, comes right out of car. The type 2 or type 3 will be exactly the same. Type 2 is not correct for any interactions. Well, because there's no interactions in here, it doesn't make any difference. If you do have interactions in your model, you want to have type 3. And there's philosophical reasons for that. Okay, let me summarize those. We get the coefficients, and if we want to calculate the LS means ourselves, we can output the coefficients and then get our coefficient matrices and then multiply them and get, well, there's the variance, there's the standard error. We can calculate each one of, these are all the LS means here. The A times coefficient. Okay, and these are the variance of the LS means, and then here's the standard errors of the LS means. So it's a little bit easier to get these. well, it's about the same as what you're doing in IML. But what's interesting here is R allows you to mix, from a SAS point of view, it allows you to mix the procs with IML. It allows you to put the procs in the IML space. This is something that really was hamstringing everybody for many, many years using IML. You couldn't bring in the procs. Well, R could do that. That's very nice. The procs are essentially the functions. So you can bring the functions into a matrix environment and then manipulate the thing. Okay, does everybody see what I'm doing here? Okay, well, if I want to get the combined interblock analysis, which is just the mixed model analysis, I'll use LMER. Okay, linear mixed effects models with a random, focusing on random effects. Okay, and this is how you write it. And we get the same analyses, we get the F-test out of this, we print it. And it's the same idea to get the standard error and the OS means and these things, and we put them all together, print them out, and calculate this stuff. So it's very similar, just we have a different function. But R is a little more work than just using Glenmix. Okay. So, which is generally the case for most things. So the questions on this? Okay. So here's another, so this is just a silly little example. Here's one where it's actually with some data from a friend of mine that works as Pioneer, Ivan. Steve Doping. Still, I think he is, working for Pioneer. And so Steve had a weak trial that he's working on. And actually, I think he was at the University of Alaska as a barley breeder and doing wheat breeding up there a little bit. I think these data come from there. This is after he's working for Pioneer. But he had a wheat variety trial with 32 varieties. So 32 entries. So the number of treatments is 32. He had 3 replicates, and he's going to have 8 incomplete blocks per replicate of 4 units each. So if you have a replicate of 32 treatments, he had 8 incomplete blocks of 4 units each. And so this gives a resolvable design. Well, we only have 3 replicates. So there's no way with only 3 replicates that you can get balance. But he used a design that we'll talk about hopefully today called now the last design, and I'll show you how to get these things. But the focus here is just on how you analyze the data. So he's most interested in the usefulness of an incomplete block and analyzing the data in the most efficient way. Okay, so I'm just reading in the data in here. I'm going to use SAS. Just read it, and I've created a new variable called incomplete block just to make sure that it's a unique variable in every replicate so you don't get lost. Okay, in other words, I like to have totally unique numbers for each block because when you print the things out, sometimes you'll get confused. If you say, oh, I have block 1 in rep 1, I also have block 1 in rep 2, and block 1 in rep 3, sometimes you print out and say block 1, here's block 1. Well, which block 1? Okay, so it's a good idea to label each of the blocks, and this is what I was doing here. So the interblock analysis here, I'm just going to use just least square, just GLM. So everything is fixed, and so I wrap an incomplete block within rep, and the entry, and LS means, and so on. And we'll talk about that in a minute. And then proc mix, then we get, or Glen mix, we can just have just what's fixed, and I'm assuming here that replicate is the only thing fixed in the model and the entry. Okay, but that incomplete blocks are random. Okay, now this kind of fits in with my philosophical reason as to why we want to have reps fixed. Why would I say you need reps fixed here? Let's people say, oh, a rep is representative of a population. Okay, well, fine, but why would I say no? It should be fixed. I haven't propagandizing people enough. There's only 3 reps. You have 2 degrees of freedom per rep. That's not really enough to put much faith in the variance component per rep. But probably it doesn't make too much difference, and you'll see it probably doesn't. But anyway, I'm assuming rep is fixed in the mixed model analysis. Here, rep is in the model statement, and incomplete block is in the random statement. So rep and entry are fixed, incomplete block is random. So here's the output. Okay, so here's my the ANOVA I wrote out earlier before. Let's just get an idea, just kind of a rough idea. What's the mean square error? What would the mean square error for block be, or for the randomized complete block design? It would be the if I can do this here, it'd be the sums of squares for about 4,000 plus the sums of squares for error, which is about 1,600. So 4,000 plus 1,600 is about 5,600. And then I'm going to add these degrees of freedom here together, which would be 21 plus, it'd be 62. So what I say, 5,600 divided by, everybody see what I'm doing? I think it turns out that the incomplete blocking doesn't make too much difference in this experiment. So remember what we had with our formula. We had b minus 1 times the mean square per block plus t minus b times the mean square per error, right, over t minus 1 times the mean square per error. Okay. And so this thing is what? This is mean square per block in this case. It's going to be, you do type 3 sums of squares, it's going to be the 20.65. And the mean square per error is what? 30, about 39, right? Or it's 38.93. Okay, so, and of course, this is 38.93. And so they have a calculator. So this B is what? This is going to be 8. 8 minus 1 is 7. So it's going to be 7 times 120 plus, let's see, T is 32 minus B. So 32 minus 8 is 24. So it's 7 times 20 is about 140. And 20, that's a large number there. Okay. And then this will be 31 times that. So this number is going to really dwarf that one. What does that mean? This number is hardly going to be any bigger than 1 at all. The efficiency is small. It turns out, you calculate the efficiency is less than 1.2. What does that mean? It means, well, maybe he's got to waste his time doing this and not the latter. Right? So that's kind of the first step. So does everything else make any sense to consider? Well, I mean, if you have such small effect of incomplete blocks, you almost could analyze it as a randomized complete block, right? Everybody see the idea? Okay, so I'm kind of splitting hairs here. You can look at the rest of it. I can almost conclude, oh, there's a huge difference between the treatments, and now let's do test of significance, just using our RCBT. Okay, but let's go ahead and look at the output from today. So here's the entry effect, highly significant as before, and now here are all the LS means. Now the LS means in this case would be a little bit larger than what they would from the blocks fixed case, or the Richter block analysis, or the GLM analysis, but not that much bigger. Okay. Okay, so the analysis will look like this, and we should have an estimated variance component here. Notice, why is that variance component 0 here? Because the mean square per block is smaller than the mean square per error, essentially. What's the mean square per block? Or the mean square per error is 39. What's the mean square per block? 20. So it doesn't look like blocks are explaining any variation, right? So when you RAML will not estimate variance component, this is what restricted means, and RAML means residual maximum likelihood. Okay, it's based on the residuals after you fit the fixed effects. And what does that force the variance component to be? If in fact the mean square of the variance component is small, it forces this to be 0. Okay, that's why that's 0. The mean square per block is less than mean square per error, so it doesn't explain anything. So what this is saying, well, you might as well use the RCB analysis. So this is another way to look at the efficiency. It doesn't give you really a number to talk about efficiency, but you can look at that, how large that variance component effect is. In this case, it's 0, so why do you look at it? Okay, the questions on this? Okay, how do we do this with R? Let's see, you have to use, you have to bring in the LS means package here. And that PBKR test, I can't remember what that's for. I'm using some function here, but I'm not seeing why. But anyway, we could, here I'm reading in, notice what I'm doing is I'm reading in an XLSX file. Okay, with that function, maybe that's where this comes from. This PBKR test is probably the, brings in the stuff, the package brings in the stuff for that read. But you can read an Excel file directly. Here I'm defining the variables as factors. It's important if they're classification variables to define them as factors. Okay, and I've identified rep number, and now here's my block. I calculated the same way, put these things all together into a data frame. And now the intra-block analysis, I'm just using LM. Okay, so this is just like the GLM analysis. Type 2, again, just as I said before, because there's really no interactions. It actually, type 2 and type 3 be exactly the same. Okay, if there are interactions, put it in type 3. And then for the mixed analysis, then use LMER. Okay. So here's the result. Here's the results of the fixed effects. And then we get the LS means that come right out of it also. I'm not sure I printed anything else. So I didn't print anything else from LMER. But LMER is mostly there to print variance components. If you do get some tests, or to calculate variance components, you do get some tests, but it's kind of difficult to fish the stuff out. But you'll get very similar LS means. Okay, if I use the LS means. Okay, so it's kind of just computational stuff, maybe not very interesting, but so the questions on this. What is computational stuff? Okay. So let me. Okay, so now we have the basic ideas of how we can construct simple block design using the computer, or you can construct them by yourself a little bit. It's simple. But I think it's worthwhile to go ahead and try to understand how some of these things are constructed. So some construction methods. Some construction methods for incomplete block designs. Now, I would like to, ideally they would be balanced incomplete block designs. Why do I want BIBs if possible? Why do I want these to be BIBs if possible?
Possible comparisons.
We can get all the variance of all possible pairwise comparisons are equal. Now, why is that? That's the best that we can do. Okay, we're being fair to our treatments. This is all based on the assumption that I don't have any preference one treatment over another. I'm trying to make them all equal, and so I want to get a BIB if possible here. Okay, the simplest construction method is what's called the unreduced BIBs. And you can get these directly. Okay, and all this is, the idea is just all possible blocks. All possible blocks. So for example, I have 5 treatments and 4 units per block. And so how do I get all possible blocks? I just take 5, choose 4. Just choose all possible blocks, all possible 4 treatments out of 5. And now what is that? Well, that's 5 times 4 times 3 times 2 over 1 times 2 times 3 times 4. And that's what? That's just 5. There's 5 blocks. We've done this. What is this one? We got 5 blocks. 1, 2, 3, 4, 5. I think this is one of the first we did. So those are your 5 blocks. Okay. So it's 1, 2, 3, 4. Then 1, 2, 3, 5. Then 1, 2, 4, 5. Just leave out here. I'm leaving out 5. I'm leaving out 4. I'm leaving out 3. Now I leave out 2. And then I leave out 1. If you go back and calculate, try to construct all possible groups of 4 chosen from 5, there they are. It's easy to get a balanced and complete block design. You just take all possible combinations. You write a little loop in your program sometimes and calculate it. Okay? Let's do another one. There's a really easy one. Kind of leads up to what we'll talk about. Let's say t is equal to 5, and k is equal to 2. So 5 choose 2 is what? 5 times 4, 1 times 2, there's 10. There's 10 blocks. How do I get them? Let's say I'm going to have start 0, 1, let's see, 0, 1, 0, 2, 0, 3, 0, 4, 0, that's it. Okay? Because I have treatments 0 through 4, be 5 treatments. Then I have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, finally 3, 4. Right? How many blocks is this? Each column is a block. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So that's an unreduced incomplete block, balanced incomplete block design. Now here's you can get this one. It's a little bit more difficult. Let's say 6 treatments, 3 units per treatment. Number of blocks is 6 choose 3. And that's going to be 6 times 5 times 4, or 1 times 2 times 3. So that's 20. It's a little more effort to get those, right? But it's the same idea. You'll just have to go through construction in that way. Okay, so there's 20 blocks. Okay. What's the problem with these unreduced BIDs? I mean, everybody likes balanced and complete block designs. What's the problem with them? They're easy to get. No problem. They're going to be powerful. They're easy to get. They're easy to understand. They're easy to analyze. They're going to be powerful. What's the downside of these?
What number of blocks of treatments?
Somebody?
What number of blocks we need is treatments?
Yeah, you're going to need lots and lots of blocks to do this. Lord, you know, Robbie has, what, 290 treatment or something. Well, maybe you don't.
1,500.
1,500, okay. So blocks of size 4, 1,500 choose 4. How many blocks is that? It's a pretty big number, right? Okay. That's the problem. Often it requires too many blocks. You can't get balanced. This is a problem with BIDs. You can't get balanced. So, well, but maybe we can get balanced if it's smaller then. So what we get is we get reduced BIDs. They have fewer blocks than unreduced BIDs. Okay. So reduced BIDs, they have fewer blocks. Okay, so let me give you an example. And it illustrates a construction method. Let's take 6 treatments again. So, question.
Got a question.
Yeah.
So you said that with the reduced you don't have balance?
We can get balance. I say in general. Right, in general, with fewer and fewer blocks, you're going to lose balance. That's what I mean. Right?
Because I thought you said with the reduced you don't get balance.
Yeah, with the reduced or unreduced, you can always get balance. With the unreduced, you can always get balance. You can get reduced BIDs, BIDs that have fewer blocks. Okay, but they're still BIDs, you see. But usually the problem is, even the reduced BIDs have too many blocks. Okay, and so what happens, you end up not being able to get a BID. Okay, so you have to use something else. And we'll talk about that. Okay, other questions? Okay, so question, can have a T equals 6, K equals 3 design, BIB, with blocks less than 20. Here, you can prove it yourself. You should be able to get this. You get this. You get this design. You should be able to do that. It's kind of painful, but you should be able to list all of them. The question is, can we get a BIB? This is a BIB now with less than 20. Well, this is called the direct construction method. Let's first of all see if we can get the BIB conditions. One of the BIB conditions is that BK is equal to RT, so I can rewrite that. So BK equals RT, I can rewrite it this way. So this means in my example, if I have, let's say B equals 10, then what does that mean? If I have B equals 10, then R is equal to 5. Can I get my balance in this case? Well, let's see. Lambda is going to be, or lambda times T minus 1 is equal to R times K minus 1. And rewriting that, I can say this over T minus 1. And R is 5, so K in this case is 3. So that'd be 5 times 2 divided by 5. This is 2, right? Okay, so that's equal to 2. So I should be able to get balance. Okay, with 10 blocks, I should be able to get balance. So can get balance with 10 blocks. How do we get it? And not going to the computer. Oh, that's ultimately what you'll do anyway. I think Jamie's finding that out. James got a problem. It's kind of an optimal design problem. Ultimately, you go to the computer, but there's good things to think about. Okay, so look, R is equal to 5, so let's get this design. Okay, let's let the columns be the blocks. So if R is equal to 5, treatment 1 is going to have to show up 5 times. Okay, and I'm going to construct this directly. So there 1 has to show up 5 times, there it is. Now 2 has to show up 5 times, but it has to show up in the same block with 1 twice. Okay? So here's the first 5. Now 2 has to show up 5 times. So here it is with 1 twice, and then it shows up by itself without 1 3 more times. Right? So how many blocks am I? I'm at 8 now. Okay, I got 8 blocks. Okay, what about 3? Well, I can do this. 3's with 1 once, 3's with 2 once, 3's with 1 once, 3's with 2 once. Right?
Question.
Yeah.
You have 1 6 times.
Oh, it should be 5. I'm sorry.
Okay.
Good, thank you. You can screw me up. Okay, so this is just 1 block here. 5 times. Okay, so how many times? So 3 is with 1, 3 is with 2, now 3 is with 1, now that it's been with 1 twice, now 3 is with 2, it's been with 2 twice, but I still need 2 more 3's, don't I? And here they are. Now that's going to fill out the blocks. Okay, 5, 6, 7, 8, 9, 10. Okay? Now I have to keep going. Okay, so 4 is with 1 once, oh, and now 4 is with 1 twice. Now let's do 4 is with 2 by itself here somewhere. You just need to think about this. So 4 is with 2. And then it has to show up, let's see, 1, 2, 3, it has to show up. Now it's got to be with 3 twice, right? Because 4 has to show up 5 times. There it is with 1 once, then twice. Here it is with 2 once, then twice. Here it is with 3 twice. Okay. Now, 5, we can do this. Well, 5 is going to have to come in these, right? Because I want to have different treatments in every block. It's got to come in there, right? Okay, so now if that's the case, I got 5 with 1 twice. I'm not even 5 with 2 yet, but let's do 5 with 3. I don't have any 5 with 3, okay? So if I do a 5 with 3, say over here, okay, now I got 5 with 1 twice, 5 with 3 twice, 5 with 2, let's see, 1, 2, 3, 4. I need one more, don't I? So I've got a choice here that 5 could, like, I'm already with 3, so I can't do that. It has to be this one, right?
Yep.
It has to be that. Okay, so now I just fill in my 6s. There, 6 shows up 5 times. Well, for smaller designs, you can do this. You can clearly see the idea. Right? Everybody see the idea how to construct these directly? Okay, it gets harder the bigger these designs get. Okay, so this is a BID. It's a balanced and complete block designed by direct construction. Okay, that has fewer blocks than 20 compared to. So this is a BID. This is a reduced BID that's obtained by direct construction. So questions on this? This is just logic. You just need to puzzle it out. A little puzzle is what it is.
Great question.
Yeah.
So how did you define that they had to show up 5 times and then 3 times in pairs?
Right here. See, this is the BID. What are the BID conditions? Remember what those are? BK is equal to RT, right? And the other one was lambda times T minus 1 is equal to R times K minus 1. So these have to hold if it's a BID. And so given all, I only have I have 6 3-beds and 3 K's equal 3, then that's going to force me to have 5 experimental units per treatment and then balance parameter 2. Okay, so it's got to be a BID. And so once I've established that, then I can use these ideas to further direct construction. Okay, here's another type of construction. Complementary construction. What's a complement? Well, if you're married, your spouse is your complement. Seems like you're just the exact opposite, right? You complement each other, right? Okay. It's the opposite. The complement is exactly the opposite. So a complementary design, what's the complement of this block? So the complementary block of this one is what? It's everything except 1, 2, 3. What's everything except 1, 2, 3? 4, 5, 6. What's the complementary block for this one? Well, it'd be 3, 5, and 6, right? 3, 5, and 6. What's the complementary for this one? 2, 4, and 6, etc. That's the complement. Okay? So you take every design that you can make, you can get its complement. So you double the number of designs that you can construct now. Okay? Look. There's another design. What's a complementary design here? What's K? What's K for the complementary design of this one? How many units per block? Okay, because I got 2 units a block. What's a complement block for this one? 5 treatments. Okay? So it's going to be what? 2, 3, 4, right? Yeah? So what's the complementary block for this one? It's going to be 1, 3, and 4. Okay? So any design you can get, you always get its complement. Yeah? What do you get when you put them together? What do I get when I put those blocks together? If I put this block together with that block, what do I get? A complete block. So what am I doing with the complementary design? I'm basically getting the other side. When I put them together, I get complete blocks. I put the 2 blocks together. See the idea here? So if you can construct an incomplete block, design, then basically you can double the number you constructed by getting the complements. And it's easy to get. So, do I need to write more here? Are there questions on this? So it's all the units. Let's see. Each block contains the treatment not in its complementary block. Complementary block. So this block here contains the treatments that are not in its complement. It's exactly the opposite. So that's easy. Once you have a design, all of a sudden you got all these others. So you see what was happening when Frank Yates, about 1935, 1940, came up with these ideas. And all of a sudden people see, oh, that's very interesting. Now let's try this. Now let's try that. All of a sudden it's just, there's this proliferation of interest in trying to identify all these different kinds of incomplete block designs. And that generated a lot of interest over the years, in developing incomplete block designs for just purely mathematical purposes. Okay, so there's another construction method called cyclic construction. It's really easy. We've also already talked about this. Anybody remember enough to tell me what the idea is for cyclic construction? Look at what this is. If I take O1, that's a generator block, and there's my blocks, and I've got, let's see, 5 of them. This would be 1, 2, 3, 4. And this would be 2, 3, 4, 0. I got to cycle back. There's my generator block. So I start with one block, and then I just cycle the numbers. So now I got block 1, 2, 3, 4, 5. Now is that a BID? Does 0 show up? Well, it shows up with 1, it shows up with 4. Does it ever show up with 3? Does it ever show up with 2? No, so it's not a BID. How do I get the rest of them? I have another generator out. And this other generator turns out to be, let's see, I think it's O2. Let's see if that's right. 1, 2, 3, 4. So O, 2, 3, 4, 0, 1. I pick up the other 2. 0's with 2 now. Right? 0's with 3 now. This is a BIB. So look, I've got 2 generator blocks. So if I generate this block, 5 blocks from that generator, and I generate this set of blocks from this generator, and I put them together, I get a BIB. Okay? These are generator blocks. If I put them together, putting both together, both sets of 5 together gives a BIB. See the idea? Okay? Yeah? How to get a little bit more complicated here. We can really go far with this idea. I'm still enamored with these things. Actually, a guy taught me math stat, a guy named H.A. David, did a lot of foundational work on cyclic designs. And actually, it turns into number theory. It turns into an area of modern algebra. So let's do one that's a little bit more complicated. So more cyclic construction. Let's say T is equal to 7, so we got 7 treatments. K is equal to 3. Oh, in this case, I didn't write it here. T is equal to 5. K is equal to 2. Right? 5 treatments in blocks of size 2. Here, let's see if I can do one, just one a little bit more complicated. 7 treatments and blocks of size 3. Okay. Well, I'll just give you this. 013 is a generator. Okay. 1, 2, 3, 4, 5, 6. 0, 1, 0, 1, 2, 3, 4, 5, 6, 0. 3, 4, 5, 6, 0, 1, 2. Okay. You don't have to use zeros. You put 7 in here and just cycle back to 1 and get 7, right? Okay. This is my generator block. Now, is that a VIB? 1 is with, 0 is with 1, 0 is with 3, 0 is with 4, 0 is with 5, 0 is with 2, 0 is with 6. All one time. This is a VIB. Right? That's a nice design. Okay. So, I mean, I can give you similar ideas with many other types of designs. Similar ideas. This is a VIB with many designs. Many other T's and K's. See how to get it? What's the question? How do you get that? All right. That's actually turns out that's not very hard. And you can see how this kind of turns into a number theory game or a kind of a big puzzle. In fact, there's sections in the American Mathematical Association where they talk about design. And we all came out of this, but they're all focused on the algebra and these kinds of things. Okay, so how to get the generators? How to get generators of VIB? For the VIBs. Well, in the simplest case, let's see if I got, if T is odd, K and T, if T is odd, K and T have no common denominators. And we have B blocks. Then we use a generator that gives all possible differences. We use generator gives all possible differences equally often. Now, what I mean by all possible differences, I'll call it this set G. And you could have a 0 difference, a 1, 2. Let's say T is equal to 7. I'm talking about this thing here. T is equal to 7. All possible differences like 0, 1, 2, 3, 4, 5, and 6. Right? I get a difference of 6. But I'm not interested in difference of 0 in my generator. If I have a difference of 0, what does that mean? That means both treatments are the same block. Okay? So if the difference is 0, if I take 0 minus 1, then that's minus 1. But what is 0 minus 0 or 1 minus 1? That means the same treatments in the same block. So I don't want this. Okay? I just want to make sure that these differences from the block, generator block, show up equally often. Okay? Now, we got a little modular arithmetic here to do this. Let's take, let's see, 0, 1, 2, 3, 4, 5, 6, and so on. Now let's go backwards. Let's see, it's minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. Okay? So here's my numbers. Minus 6, minus 5, minus 4. Now what does that map to in mod 7 space? Of course, this is 0, 1, 2, 3, 4, 5, 6. Then I got 7. This would be 6, and then 0, 1, 2, right, so on. What are these back here? What's minus 1 map to? Going backwards now. What's that one map to? 6, right? What's that one? 5, 4, 3, 2, 1. I got minus 7. What's that map to? 0. Okay. Now, why do I need to do that? Because I'm going to take all possible differences of my generator here. Okay. So let's take my generator. I'll take my generator 0, 1, 3. Now let's take all my differences. I can take O minus 1 is what? Minus 1. I take 1 minus 0, that's equal to 1. So minus 1, what is minus 1 here? I got a 6. So if I go up here, minus 1 maps to 6, right? Okay. How about if that's 0, 1, 1, 0? How about O 3? So it's going to be O minus 3 is minus 3. What's that map to? 4, right? So that's 4, and maps to 4. And 3 minus 0 is 3 by itself, right? See what I'm getting to here? Now 1 minus 3 is minus 2. What's that map to? 5. Okay. And 3 minus 1, let's see, wait a minute. 3 minus 1 is 2. So now look, I got all my numbers here. They all show up equally often, right? I got 1, 6, 3, 4, 2, 5. All those differences show up equally often. And that makes sense. That tells you that it's going to be balanced. It tells you that those differences, all those differences are going to show up someplace in the design. Okay. Everybody see what I'm doing? This should be easy to see. If I just take my generator here, and I take 0 minus 1, I get minus 1, and it maps to 6. 1 minus 0, it just maps to 1. 1 is 1, right? So on. Okay. Okay, so that's enough at least for some of these more abstract methods. So there are questions in this? So I'm talking about lattice designs now. Lattice designs. And usually these designs come up when we have a number of treatments that are much larger than the block size. Number of treatments is much larger than block size. This is how they're usually used. Robbie just said, I got 1,500 entries. I got 1,500 treatments in block sizes of what, 20? George likes 20 or 30 in his blocks. Okay? He's got, T is 1,500, K is 20. Yeah, he needs to deal. There's many situations like this where you're screening, the screening type design, where you have many more treatments than you have block size. Okay? And these are called the lattices. Now the first one I want to talk is a balance lattice. Where when let's say a standard balance lattice, I'm going to assume that the number of treatments is just a square block size. Okay? And so what does that mean with the size of these things? It's just kind of getting a dimension. If I look at K and T and R, these are for balance lattices now. I'm not going to drive this stuff. And then B. So let's say if it's 3, then I have 9 treatments in block sizes, but 9 treatments in block sizes of 3. This requires 4 reps and 12 blocks. Here are these balance lattices. Not only T is equal to K squared, but also it's possible to show the number of blocks you need is K squared plus K. So how about 4? 4, this is going to be 16, you need 5, and that's 20 blocks, total blocks. So 5, 25, this is 6, and 30. and so on. So these are the balance lattices. So if I have 25 treatments in blocks of size 5, then I'll need 6 reps with 30 blocks. Okay. Now, in Angela Bastidas' case, she had 25 treatments in block sizes of 5, but she certainly didn't have enough field to get 6 reps. Okay, she couldn't do that. Not only that, she had factorial structure. So the lattices here are assuming that there's no factorial structure at all, that we're just looking at the differences between all treatments. Okay, so balanced lattices are for these situations. Now, how to get these balanced lattices? How to construct. We can use the idea from confounded factorials very nice here. So I'll say how to construct. Use ideas from confounded factorials. Okay, so say for example, k is equal to 3 and t is equal to 9. What I can do is I can use a 3 squared series. So I can use a 3 squared confounded factorial in blocks of size 3. Okay? When I assume that my treatments are 9 treatments here are arbitrarily assigned to the treatments that I have. Okay, so for example, I'm trying to use this board here, because I'm going to put down the screen here in a second. I might take out my treatments out here. There's 9 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9. What I can do is I can make my treatment combinations, A, B treatment combinations I got 3 levels for A, 3 levels for B. I could say, okay, 0, 0, 0, 1, 1, 1, 2, 2, 2. And 0, 1, 2, 0, 1, 2, 0, 1, 2. All right? So here are my treatments. I have no structure among my treatments. What I'm going to do is I'm going to say, okay, these are called pseudo-factors. Pseudo-factors. Pseudo-factors are only there to help you assign your treatments to blocks. Okay? Now, if I think of my total treatment combinations, what do I have? In my ANOVA, I got 2 degrees of freedom for A, 2 degrees of freedom for B, and then the interaction is 4. 2 degrees of freedom for B, and then I break up the interaction to AB1, that's 2 degrees of freedom, and AB2, that's 2 degrees of freedom, right? There's my 8 degrees of freedom. Now, if I want to have my design in blocks of size 3, how many effects do I have to confound? Ashley. Remember, if I got a 2, let's see, I got a 2 cubed, I want in blocks of size 4, what do I have to do? One of those effects has to be confounded to break the 8 into 2 groups of 4, right? If I'm in blocks of size 4, I have to confound one effect, right? Well, in this case, I can just have confound one of the effects, but it has 2 degrees of freedom. So I'm going to have to confound one of these effects with incomplete blocks in each rep. Okay, so confound one effect with incomplete blocks in each rep. Well, if I partially confound it, what did I do? I have to confound AB1 with blocks in 1 rep, AB2 with blocks in rep 2, A with blocks in rep 3, and B with blocks in rep 4. Okay? And so that's what we do to calculate balance of lattices. So hopefully this will make sense. All right. So I confound A. Let's see, I can't remember how I did it first. So I randomly, in the handout I've given you, I got my treatments here. And these treatments could be anything. I'm just making up this factorial stuff to allow me to assign my treatments. take the blocks. You know, that's the whole idea here, is which blocks to assign to which treatment. Okay, okay, so here's I define my treatments. 1 to 9, there they are, and here's my C code, right? Now I got my mod equations. I set my mod equations up like we've done. And so for the first one, I'm just going to confound A. Okay, there's my mod equation with A. Second one, I'm going to confound B, right? Third one, I'm going to confound AB1. That's the mod equation. The fourth one, there's AB2. So once I identify my mod equations, I get my block. So what I'm going to do is confound. Here are my blocks, blocks 0, 1, and 2 in rep 1. And so here it is. Okay, okay, so for rep 1, here are the 0, 0, 0, 0, 1, 0, 2. There they are. And the blocks are going horizontally now. Right? Now look, these numbers, once I get that rep, these numbers don't mean anything. I'm just using them to decide which treatments go to which block. So I go back and map. 0, 0 is what? 0, 0 is 1. Right? Now I go, but these are my treatments I'm really interested in. 1, 2 is what? 1, 2 is 6. Right? So now I've got my 9 treatments. So Ronnie's got 9 genotypes. He didn't have any factorial structure. Okay? He just uses this as a clue to get his 9 genotypes there. Okay? Now, so what I've done is I've partially balanced. So I partially balanced A, partially confounded A with incomplete blocks in rep 1, B with incomplete blocks in rep 2, C with incomplete blocks in rep 3, and, or not AB1 and AB2 with incomplete blocks in rep 4. Now notice, there's 4 reps. Why? That's how many facts I have available to confound into my confound factorial. Okay. Okay, questions on this idea? Okay, that comes directly out of confound factorial. So once you understand that, you should be able to construct balanced lattices without a problem. These are VIDs, and you can go back and check yourself to make sure they're VIDs. One thing that's interesting about the structure you get from these, notice I showed right that when we first started talking about incomplete block designs, look, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm labeling across the rows of the blocks now. I go to the next rep. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going down across. Notice what the third one is. I'm going 1, 2, 3. Let's do it a little bit differently. It's kind of, let's see. No, you really can't see it, but it goes, these are diagonal. Well, I really can't see it now. But I'll stop right now. But anyway, you can see some pattern in these blocks that come directly out of the confound. Okay, so next time we'll finish talking about lattices. There's different kinds of lattices. I'll show you how to get alpha lattices, which is what Steve Doping was using, but we probably gave you. And then we'll talk about more general types of incomplete block designs, and hopefully move on to designs that have 2 blocking factors. We'll call them. And I'll see you next time.